Hi, this is lecture 17 of EP1. In this lecture, we will continue thinking about rotations. In the previous lecture, we discussed rotations and how to describe them. We talked about angles, angular velocity, angular acceleration. And today we will think about the causes of rotational motion. So how can I find, if I know all the forces that are applied to an object, how can I find acceleration? So that's the main subject of today's lecture. You probably remember from the first few weeks that if you have an object and if this object has some mass, then in order to move it with acceleration, you need a net force. And if you have a net force, unbalanced force acting on it, then its acceleration can be found using Newton's second law, which says force is equal to mass times acceleration. When it comes to rotations, we have a very similar equation. And this equation tells you that if you have an object, let's say this is an object, and it is fixed at one point so that it cannot move around, but it can still rotate around this pivot point, then if there are forces applied to this object, so let's say there is this force that pulls this way, then to find angular acceleration, what you have to do is you have to find the torque, the net torque, and then net torque is equal to moment of inertia times angular acceleration. So when it comes to rotations, instead of force, you have a torque, and instead of mass, you have moment of inertia. Torques make objects rotate, and the moment of inertia, or rotational inertia, is something that describes how difficult it is to rotate things. It's kind of like when we had mass, and the mass was telling us how difficult it was to get things moving, or to impart some acceleration on them. So let's discuss these components separately. Let's start with the torque, and then let's see how torque works and how to compute it, and then let's see how the moment of inertia works and how to compute it. So now I'm on slide number 3 in my lecture slides, and on this slide, what I have is I have some sort of object that looks like a rod. I have this rod, and there are a number of forces applied to this rod. So you have, this is the pivot point around which this rod can rotate. There is force F1 applied here, and there are a bunch of other forces. There is force F2, slightly further away, forces F3 and F4. And there is this force of 5 right here. So how do we compute torque? Torque is something that compels, makes objects to rotate. To compute torque, so first of all, let's think about this intuitively. This is something that we all know from everyday experience. If you think about this arrangement, I would like you to think about this arrangement for a few seconds and think about which forces would cause the most rotation for this rod. What I will do is I will pause here for a second and you think about this, and then we'll pause your video and then come back. Okay, so we have this rod and we have 5 forces. Now let's start with the more obvious cases. Let's look at force F1, for example, if you look at force F1, I think it's clear that this force F1 cannot really rotate this rod because it's applied at the pivot point. The same thing is true for force F5. Force F5 is not applied at the pivot point, it's applied here, but its direction is aligned with the rod. So if you just pull on this rod, it will try to move the rod to the right. And if the rod is attached here, then it's not gonna move, but this force F5 cannot cause a rotation. Now let's look at forces F2 and F4. Let's say forces F2 and F4 are roughly equal in magnitude. Then you probably know from your everyday experience, opening the doors and stuff like that, that force F4 will be more effective in rotating this rod compared to force F2. And that's because force F4 is applied further from the pivot point. You can check this by trying to open the door by pushing on it closer to the hinges and further away from the hinges, and you will see that closer to the axis of rotation you are, the more difficult it is to rotate an object. Now let's think about force F3. Let's compare F3 to F4. Again, let's say they are roughly equal in magnitude. Then again, based on intuition, I think it's not that difficult to believe that force F3 is more efficient in rotating this rod than force F4, because force F3 is perpendicular, exactly perpendicular, and force F4 makes some angle. So we saw before how force F5 was not very effective at rotating the rod because it was aligned. Force F4 is kind of midway. Some part of it is some part of this force is aligned with the rod. Yeah. And so this projection doesn't contribute anything useful to the rotation, and it's only the second projection, this projection of the force, which is perpendicular to the rod, that actually contributes to the rotation. So to summarize, for this specific case, we have forces F1 and F5 that give us zero torques for different reasons. And then we have forces F2 and F4, and F4 provides more torque than F2, so torque 4 is more than torque 2, even though the forces are roughly equal. And then if we look at forces F3 and F4, we kind of agreed that torque due to force 3 is larger than torque due to force 4, because force 3 is pointing in a direction that's the most efficient for the purposes of rotating the rod. Now we can put all of this intuition in one formula, and this formula is that the torque is equal to the force times how far away from the pivot point the force is applied, times the sine of the angle that this force makes. So let's think about what each of these mean. Let's start with the force. I mean, it's clear that if you have more force, you have more torque. So this R is different from the pivot point. Again, let me draw this rod over here. This could be a door, for example, a top view of the door. And then this R tells you that further away you apply your force, more efficient this force is at rotating things. So this force would be the most efficient force at rotating things. And then we have this angle here. So the angle, we have sine of the angle. And from your calculus or trigonometry, you probably remember that sine of 90 degrees is 1. And sine of 0 degrees is 0. So if your force is aligned like so, if there is 0 degree angle, then this force will produce 0 torque. And if the force is like this, if it makes a 90 degree angle, then the sine is 1. And since sine for any angle is between 0 and 1, it can never be more than 1. And it can, well, it's between -1 and 1. This means that the most optimal degree angle that you can make to rotate objects is the 90 degree angle. So this is the key formula. Every time you have some forces and you want to compute their torques, this is the formula that you use. And to compute the torque, you need 3 things: magnitude of the force, where the force is applied, and what kind of angle this force makes with the direction of rotation. Now, one more thing to keep in mind is the direction of your torque. So when you have forces, you know that forces are vectors. They could be pointing in any of the 3 directions, x, y, z, or somewhere in between. With the torques, when you have an object, let's say I have this disc, which has a pivot point in the middle, then if I have torques, when it comes to the directionality of the torques, I have 2 options, right? My torques could be attempting to rotate the object clockwise, or they could be attempting to rotate this object counterclockwise. Those are the only 2 possibilities once the pivot point and the axis of rotation are fixed. And when we do math, those 2 torques must contribute with the opposite sign. And it's the standard convention is that if you have a torque that tries to rotate things counterclockwise, you call that a positive torque. And if you have a torque that tries to rotate things counterclockwise, you call that a negative torque. Okay, so to summarize, this is the formula for the torque, and we have to be careful about the signs, plus signs and the minus signs. Now let's move to the second component in that equation, which is moment of inertia. Moment of inertia, usually denoted by capital letter I, is kind of equivalent to mass for the linear motion. And a moment of inertia tells us how difficult it is to rotate objects. Again, let's start with developing some intuition. Let's say I have some sort of mass on a rod, and let's say I'm trying to rotate it clockwise around this point. The question is, when is it more difficult to rotate this object, and when is it easier to rotate this object? And if you think about it, one thing that makes a difference is the mass. So if this object is heavy, it will be more difficult to rotate it. But mass is not the only thing that is relevant here. It also matters how far away this mass is from the axis of rotation. And it's easier, the way it works is that it's easier to rotate things if mass is close to the axis. And it's more difficult to rotate things if mass is further away from the axis. So the second object, object B, given equal masses, would be more difficult to rotate compared to the first object, this object A. And this is also probably something that you know from everyday experience. You can try it by, I don't know, by attaching something to a rope and trying to rotate it, and you will see that the longer your rope is, the more difficult it is to rotate those things. So the formula for moment of inertia is that moment of inertia is mass times radius squared. So heavier the things are, more difficult it is to rotate them, but it also matters how far away they are from the axis of rotation. This formula is true for when you have point-like objects. And we will, in a little bit, we will talk about what to do when you have extended objects. So what I would like you to do now is I would like you to look at the bottom right corner of slide number 4. In that corner, I have 3 objects. One of them is 36 kilos, and it's 1 meter from the axis of rotation. The second one is 2 meters away from the axis of rotation and weighs 9 kilos. And the third object is 3 meters from the axis of rotation, and it weighs 4 kilos. And here I didn't necessarily draw them to scale. This should probably be shorter. Okay, like this looks better. And the question is, which one of these objects is more difficult to rotate? So why don't you think about this, pretend it's an iClicker problem, pause the video, and when you have an answer, go back to the video. Okay, so the question is which one is more difficult to rotate, and to figure that out, what I want is I want to compute the moment of inertia, because this is the quantity that tells me how difficult it is to rotate objects, to angularly accelerate objects. Moment of inertia is mass times r squared. I will compute it for all 3. For the first object, I have 1 times 36 squared. Sorry, mass is 36. I have 36 times 1 squared. This is 36. For the second object, I have 2 times, wait, mass is 9. Okay, 9 times 2 squared. This is 4 times 9, 36. Yeah, 36. And for the third object, I have the mass is 4. 4 times 3 squared. 3 squared is 9. 9 times 4. That's also 36. Okay, so let me double check my numbers. No, I think that's correct. Okay, so it looks like all 3 objects are equally difficult or equally easy to rotate. And it could be counterintuitive at first because the first object weighs 36 kilos. That's a pretty heavy object. And the third object is just 4 kilos. So it's like 9 times lighter, but it's also 3 times further away from the axis of rotation. And the distance is squared in this formula. So you are more sensitive to distance than you are to the mass. If you double the distance, your moment of inertia will go up 4 times, while if you double the mass, your moment of inertia will only go up by a factor of 2. So this is formula for point-like objects. This formula is pretty simple. It's also simple to generalize it if you have many point-like objects. So let's say I have a rod, and on this rod I have 1 mass attached here, and the second mass attached here, and the third mass attached here, M1, M2, M3, and some distances R1, R2, R3. If that's the case, what you do is you simply add moments of inertia of all your point-like objects. So I would compute the moment of inertia of this, of that, and I would simply add them up. So to write it in a single formula, the moment of inertia is just a sum over all individual moments of inertia. So this is good, but what if, you may ask, what if you have some sort of extended object? Let's say you have a book which looks like a rectangle, and you are rotating your book around this point. What's the moment of inertia of this book? So this is slightly more complicated. What we do in this case is, and this is described in your book, so I would encourage you to go over description in the book. What we do is we divide this book into small parts, so many small parts. Each small part has its own mass, and it's some distance away from the axis of rotation. And so what we will do is we will compute the moment of inertia of each one of them, and then we will sum it up. And when you have very small numbers that you add up, that's an integral. So there is some sort of integral that gives you the moment of inertia of extended objects. And if you're interested, I'm not going to make big deal out of this. I'm not going to ask you to compute integrals to find moments of inertia of objects. But if you're interested, please check it out in your textbook. And in the end, for simple shapes like a sphere or a spherical shell or a rod or a cylinder or a rectangle or a ring or a disk, for those simple objects, the formulas exist. Those moments of inertia have been computed. If you need them in your homework, just look them up. There is a table in your textbook. You can look it up in the textbook. So for example, you can see that if you have, I'm looking in the textbook now, and the textbook tells me that if I have a solid sphere, a solid sphere that has a radius r, then the moment of inertia of the solid sphere is 2 over it's 2 over 5 mr squared. So to summarize, it would be nice if you knew how to compute moments of inertia for arbitrary bodies, but you're not going to need it for this class. Every time you have a body and you need its moment of inertia, you can just look it up in the table. So let's look at some sample problems that may involve torques and moments of inertia. On slide number 5, I have a few pictures. So one of them is a pulley that has mass m, and there is a box of mass small m suspended from it. The second example is, again, a pulley that has some size and some mass, and you have 2 objects suspended from it on both sides with masses m2 and m1. And then you have the cylinder, and there are multiple forces acting on the cylinder. The second and the third cases are actually also in your homework. So let me start with the cylinder. This is one of your homework problems. So you have a cylinder and you have 4 forces applied to it. And let's say what we need to do is, let's say they ask you to find angular acceleration. So how do we find angular acceleration for this cylinder? The key equation for us is the Newton's second law, which tells us that the torque is equal to, net torque is equal to moment of inertia times angular acceleration. So to find acceleration, what you need is you need to know your moment of inertia and you need to know your net torque. Let's start with the moment of inertia because that's kind of simple. So moment of inertia of a cylinder, you don't need to compute it. You can just look into the table. I'm looking into the textbook now. I'm looking at this table of moments of inertia of simple shapes. And it tells me that if I have a solid cylinder and if it's rotating around its central axis, then its moment of inertia is 1 over 2 mr squared. So the moment of inertia of a cylinder is half mr squared. Okay, so this we found. Now let's find the torque, the net torque. To find the net torque, I need to add all the torques. So torque 1, torque 2, torque 3, torque 4. And just to remind you, torque due to a force is force times the distance from the axis of rotation times the angle. So let's look at the cylinder and all the forces. And you know, my drawing isn't that good, so please have a look at the slides. Let's start with force F1. Force F1 is trying to rotate the cylinder counterclockwise. So force one, torque 1 comes with a plus sign since it's counterclockwise. And what I will do is I will take force 1, I will multiply it by my radius because this force is applied at the rim. And then I need an angle. The angle in this case is 90 degrees. Sine of 90 degrees is 1. So this is just F1 times R. I will do exactly the same thing for force number 2. So I have force number 2 times R, because it's also applied at the rim. Angle is 90 degrees. The only difference here is that my second force is trying to rotate me clockwise, so I need to put a negative sign here. Let's move to force 3. For force 3, again, I have a negative sign because it's rotating me, trying to rotate me clockwise. I will have force 3 times R. So keep attention to this R. This R is different from the radius because the force is applied at a point that's inside the cylinder. And my angle is 90 degrees, so this is multiplied by 1. And now I have force F4. So I will have F4 times R because this force is also applied at the rim. And now I have the sine of 0 degrees. I have the sine of 0 degrees because this force is aligned with the line that connects it to the axis of rotation. The sine of 0 degrees is 0, so this force doesn't contribute any torque. And if you think about it, it makes sense. The way this force F4 is directed, it's not gonna result in any rotation. So this is my net torque. To find my net torque, I just added all the torques, and I was very careful with the signs. And to find the angular acceleration, you have to take this net torque and you have to divide it by the moment of inertia, which in my case is 1/2 mr squared, because this object has a cylindric shape. I will not discuss this problem if you have this homework problem right now, because I'm kind of running out of time. But if you have any questions about this problem, please join our Zoom help room on Friday at 12:30. Basically, what's happening here is that the basic idea is that you have this pulley, and this pulley has some moment of inertia, and there are 2 torques acting on this pulley. One torque is due to this rope that has tension T1, and the second torque is due to this rope that has tension T2. Both of them are applied at the rim, and both of them are making 90-degree angles. So the net torque in this case will be T1 times R minus T2 times R. And this net torque to the moment of inertia times angular acceleration. Now I put a minus sign here because T2 is trying to rotate me clockwise, and there was a plus sign here because T1 is trying to rotate me counterclockwise. So try this out on your own, and if you have any questions, please join the Zoom help room on Friday.